Car, traffic signs, street lights, fences, appliances, these steel products are designed to make life easier. But have we ever wondered why they don't rust away over time? Well, the secret is in a thin layer of zinc, a powerful coating that protects steel from corrosion, ensuring that this everyday essential stays strong and reliable for years to come. This protective coating is especially noticeable in the dull grey color of this post, applied to an industrial process called optic galvanizing. Today, I'm going to show you how my research contributed to make this process more efficient while reducing its environmental impact. The op-dip galvanizing process consists in dipping a metal strip into a bath of molten zinc and then withdrawing it vertically at constant speed UP. The zinc entrained by this movement forms a thin liquid layer, which later solidifies into a corrosion-resistant coating. While still liquid, an impinging gas jet removes excess zinc to ensure the desired final coating thickness. Withdrawing the strip too quickly can cause the jet to oscillate, leading to undulating waves in the liquid, which result in reduced final product quality and the need for additional surface treatments. To cope with this problem, a solution with a feedback regulator has been considered, where a series of actuators interact with the liquid film to reduce the amplitude of the undulation waves based on observation of the liquid film thickness from a set of sensors and following a control logic embedded in a controller. The goal of this project is to develop an optimal control logic for the controller to minimize undulation waves using gas jet and electromagnetic actuators. To achieve this goal, we addressed three main research questions. Where should we place the observation point? Can we simplify the governing equation to facilitate our analysis? And how can we design an efficient control law that performs well under different conditions? To position the observation points, we studied the impulse response of the liquid film. So imagine a flat liquid film perturbed by an actuator. This disturbance generates waves that evolves over time in a ways that depends on the film thickness. In a film, the entrainment of the substrate causes the waves to be convected upwards, whereas in a thick film, gravity causes the waves to be advected downwards. Between these two extremes, there must be a range of liquid thicknesses where these waves spreads throughout the entire domain, showing absolute instability characteristics. By solving the linearized Navier-Stokes equations, we identified this window of absolute instability in the space of Reynolds number and non-dimensional film thicknesses. However, as we can observe, the condition of optic galvanizing lie well outside this region. This means that when we perturb the liquid film at a specific point, the disturbances will be carried upward. Based on this result, we can safely place the observation point upstream of the actuators, as their influence won't be captured by the observations, which we only observe the incoming undulation waves. So we now turn our attention on the simplified liquid film equations. The 3D liquid film affected by gas jet and electromagnetic actuators is governed by complex magneto-hydrodynamic equations, which are computationally demanding and challenging to solve. So, to circumvent this problem while retaining the key physical characteristics, we developed a simplified model for the liquid film. This model consists in a system of equations in terms of the liquid film thickness H and the flow rates Q, where F is the flux matrix representing the convective effect, and S is the vector of source terms accounting for gravity, the shear stress at the substrate, surface tension which acts as a restoring force that brings the liquid film back to a flat state, the external actuators exert the influence through a pressure and shear stress distribution at the free surface, as well as a Lorentz force for the magnetic actuators which pushes the liquid downwards. With the observation positioned and the mathematical framework defined, we now derive the optimal feedback control law to manage the actuators based on liquid film observations. The optimal control law can be derived using two different approaches. white box and black box. A stability-based approach white box, the equations of the simplified models are fully known. The control law is derived through linearization and optimization, aiming to determine the optimal feedback coefficient that ensure that the liquid film is always linearly stable. In the black box machine learning approach, the governing equations are hidden in a black box. The only way to interact with them is by passing action and receiving observation of the liquid film, along with a reward function that indicates how well the control action is performing. Based on this information, a new action is selected using a feedback control law provided by a neural network, whose weights are updated through a reinforcement learning algorithm to improve the controller performance over time. The advantages of stability-based approach resides in its speed, efficiency, guaranteed system stability, and can rely on a large body of established literature. However, it is limited to the linear dynamics of the system, is applicable only when waves have small amplitudes, and relies on predefined models. It also struggles with real-life conditions involving uncertainty and noise. On the other hand, the black box approach is independent of the model, can handle nonlinearities and adapt easily to varying conditions. However, it lacks stability guarantees, is sample inefficient, requiring many liquid film simulations to learn the control law, and demands significant computational resources. Based on these considerations, we thought of combining the two approaches, using the machine learning approach to handle large amplitude waves, and then switching to the stability-based approach once waves become small enough. To evaluate the performance of the linear stability-based controller, we applied it to control a highly unstable liquid film, one much more unstable than what typically encountered in the undulation problem. In this scenario, waves go down the film while increasing the amplitude. As we can see, the control action beginning at t=10 and within a limited amount of time, the actuators bring the liquid film to a flat state. Even after the film is flat, the actuators continue to operate as it is an unstable equilibrium. So moving now to the machine learning control for the large amplitude waves. We consider a setup with 2D gas jet and electromagnetic actuators working together. We can see the 3D evolution of the controlled liquid film, its 2D color plot, the evolution of the gas jet intensity shown by the blue line, and the magnetic field intensity shown by the red line. Additionally, we have a plot along a line comparing the control case with the uncontrolled one. The interaction of the actuators with the undulation waves is evident. The gas jet pushes the crest, while the magnetic actuators lift the valleys through the Lorentz force. This complementary control strategy reduced the amplitude by 15 to 20%, which is an excellent result considering only 2 actuators are used. To wrap up, in this research we have seen how we address a complex industrial problem using interdisciplinary approach, which allowed to answer both theoretical and practical research questions, leading to a sizable reduction of the undulation amplitude. However, the result and the method developed in this research have application beyond the field of coating flows. For example, the magnetic model can be easily adapted to study liquid metal walls in tokamak nuclear reactors. The analysis of absolute and convective instabilities offers valuable insights for a wide range of fluid systems. Additionally, the control methods developed can be applied to falling film heat exchangers, flexible electronics, and liquid Gallistan application. And last but not least, an experimental campaign is planned to take place at the von Karman Institute, where a flow Gallistan will be controlled by some magnetic actuators with a control law based on the result of this research. This research showed that the feedback regulator can enhance the optic galvanizing process, improving efficiency and sustainability. By developing an optimal control law for the feedback regulator, we minimize the undulation instability, allowing for higher production rate and reducing the environmental impact of the process. The results and method introduced open new venues for research across fields, paving the way for further advancements.